In this video, we're going to conclude our discussion of automatic memory management with the third and last technique we're going to talk about for garbage collection called reference counting. So the basic idea behind reference counting is that rather than waiting for memory to be completely exhausted, we're going to try to collect an object as soon as there are no more pointers to it. So as soon as we discard the last pointer to an object and it becomes unreachable, we will try to collect it at that point in time. And how can we do this? Well, as the name suggests, we're going to count the number of references to each object. So in each object, we're going to store the number of pointers to that object. So if I have an object in memory, and it has, say, 3 pointers to it from other objects, then somewhere in this object is going to be a dedicated field that contains the number 3. And if this number ever drops to 0, if we discard these pointers and this number becomes a 0, then we know that nobody's pointing to this object and it can be free. And what this means is that every assignment has to manipulate the reference count in order to maintain an accurate count of the number of pointers pointing to an object. So allocating a new object returns an object with a reference count of 1. So when an object is created by new, it will already have a reference count of 1. The pointer that is returned is the only reference to the object. And so we're going to write the reference count of an object x as rc of x. And now when we have an assignment, x gets assigned y, we're going to have to update the reference counts of both the object that x points to and the object that y points to before the assignment. So what happens here? So if y points to p, so let's draw our objects here. So y is a local variable, and it points to some object p in memory, and x is also a local variable, and it points to some object o. Okay, so now x is getting the value of y, and so that's going to move this pointer from where it pointed before to point to the same thing as y. So what's going to happen? Well, p's reference count is going to go up by 1, and o's reference count is going to go down by 1. And since we decremented o's reference count, since we dropped this pointer to the object o, we need to do a check to see if the reference count has become 0. And if the reference count has dropped to 0, then we can free the memory for o. And then, in addition to updating the reference counts and checking whether the reference count of o became 0, we actually need to do the assignment itself. All right, so every assignment, I want to stress that, every single assignment in the program gets now translated into these 4 operations that need to be done to maintain the reference counts. There are trade-offs in reference counting. It has advantages and disadvantages. One of the big advantages is that it collects garbage incrementally without large pauses in the execution. So for applications where large pauses would be problematic, say real-time applications or interactive applications, reference counting can really help because it minimizes the length of the longest possible pause. Okay, so your program will never go to sleep and just appear to stop running for some period of time because it's off collecting garbage. It always collects the garbage in small incremental amounts, and so you never see a long pause. Reference counting, or at least a basic implementation of reference counting, is also quite easy to implement. It's very straightforward to go through and modify the code to add reference counts, and you can easily imagine a code generator that would simply generate different code for the assignment operation than it normally did if you were adding reference counting to an implementation. So really the changes that are needed for a simple implementation of reference counting to a compiler are not that pervasive. Now, there are some disadvantages to reference counting. One is that manipulating the reference counts at each assignment is really quite slow. So if you remember what happens, we have a couple of updates to reference counts. So we have to update, the reference count of 2 objects to do this is the code to do an assignment, and then we have an if statement, and then we actually do the assignment itself. So there's 2 reference count updates, a test to see if a reference count became 0, and then we actually do the assignment. So the overhead here is substantial. You're taking every single assignment in the program and blowing up its cost by at least 4 or 5 times, and that will have a very noticeable impact on the performance of many programs. Now, it is possible to optimize reference counting. So for example, if we had 2 updates to the same object, say within a basic block or even within a control flow graph, A compiler, a smart optimizing compiler, could frequently combine those reference count operations together. So instead of updating the reference count of the object 2 times, it could just update it 1 time. And similarly, if there were even more reference count updates to the same object, potentially all of those could be coalesced within some region of the program. The problem with that is that it becomes very tricky to get that right. So a simple implementation of reference counting is quite slow, but easy to get right. A very sophisticated implementation of reference counting or highly optimized implementation of reference counting is somewhat faster, still has a noticeable performance impact if you're reference counting all objects, but it is substantially faster. However, it's quite tricky to get it correct. The other problem with reference counting is that it cannot directly collect circular structures. So to see this, let's draw a little heap with a circular structure. And so let's say we have a local variable x, and it points to some object in the heap. And that object has a pointer to another object. All right, and that object, that second object, then has a pointer back to the first object. Okay, so here x is pointing to, say, a circularly linked list of length 2. All right, and if we add in the reference counts here, what would those look like? Well, this object down here, the second object here has only 1 reference to it, so its reference count would be 1. And this first object has 2 pointers to it, 1 from x and 1 from the other object, and so its reference count is 2. Okay, so here is our little heap, and we can see that there's no garbage here because all the objects are reachable from a local variable or a variable of the program. Now, if we were to assign a new value to x, let's say that we had the assignment x gets null. All right, so this pointer goes away. Well, what's going to happen? Well, when we do that assignment, we're going to change the reference count here of this object. It's now going to be 1. And if we look at this heap, we now see that these objects, these 2 objects are unreachable. Okay, so these are unreachable. But notice that their reference counts are not 0. So we can't collect them. The garbage collector or the reference counting implementation will check the reference counts and see, oh, these are 1, and so we can't delete them. And what it can't see is that the only references to these objects are from other unreachable objects. So the bottom line is that reference counting can't collect circular structures, and there's only really 2 ways to deal with that. One is that the programmer remembers whenever a circular structure is going to become unreachable to somehow break the circularity. So for example, if before we clobbered the pointer to x here, we remembered to go in and say set this pointer here to null. If we nulled out 1 of the pointers in this cycle so that there was no longer a cycle, then the reference counting would work correctly, because then the reference count of this object would go to 0 when this pointer was dropped from x, and that would cause the reference count of this object to also go to 0 after this object was deleted. Okay. The other possibility is to back reference counting by some other garbage collection technique that can collect cycles. And so in some reference counted systems, for example, most of the garbage collection is done by reference counting, but every now and again, once in a very great while, you might run a mark and sweep collector to go through and clean out any circular but unreachable data structures. We're now ready to wrap up our discussion of automatic memory management, and so I just want to make a few high-level points here. First of all, there's no question that automatic memory management is a great thing. It prevents very serious storage bugs, some of the most difficult bugs in programming. And when you're writing in a garbage collected language, you really have just a whole class of things you don't have to worry about. And so it is certainly a more productive way to program. So if your program is really a good fit for automatic memory management, then you'd be crazy not to use a system that provided that kind of support. Now, the disadvantage of automatic memory management is that it reduces programmer control. So you don't have control anymore over the layout of data in memory, and you don't have control over when the memory is deallocated. So you neither have control over where the data is in memory, and you have only a very limited amount of control over how much memory your program is using. Okay, and so if these two things don't matter, if your application is not extremely data intensive, where the precise layout of data in memory and how much data is residing in memory is important, then garbage collection will likely work very well. But there are applications, particularly high-end data processing and scientific applications, which use a lot of data and need to make very, very efficient use of the memory, where garbage collection actually becomes too inefficient to do a good job, and people in those domains still use manual memory management. But there are some other issues. So in real-time applications, the pauses can be problematic. So if you have a program that needs to meet guaranteed deadlines, many embedded systems that are interacting with the outside world, say controlling dangerous machinery and things like that, they have to have response times that are guaranteed to make sure that nothing terrible happens. And introducing a automatic memory management system that might pause for arbitrary amounts of time, makes that a very problematic thing to guarantee. So you don't always see garbage collection used in real-time applications, although there has been a lot of progress in the last several years on real-time garbage collectors. Another issue that every programmer who uses automatic memory management probably will have to face is the problem of memory leaks. So while automatic memory management prevents you from corrupting your memory, it really doesn't prevent you from hanging on to too much data and possibly affecting the performance of your program dramatically. So memory leaks are possible in garbage collected languages, and I would say they're even likely. I'd say that the fact that you're not as aware or not as forced to be as aware of how the memory is being used makes it easier to have memory leaks. And the kind of memory leak that you will have in, say, a Java program is that you'll have some variable, say x, that points to some data structure, and this data structure is gigantic. Okay, so let's say that this is the abstract syntax tree in a compiler. All right. Now there may come a point in the computation where you don't need the abstract syntax tree anymore. So let's say that we have converted to an intermediate language and from the abstract syntax tree, and now all of our processing for the rest of the compilation is going to be on the intermediate language representation and generating code from that. And we never go back and look at the abstract syntax tree again. Well, the compiler, the garbage collector doesn't know that you're not going to use the abstract syntax tree again in the future. And if you have a variable that's pointing to this gigantic data structure, even if you're not using it, it's going to hang around and is going to be using up memory. And so the right thing to do is when you reach a point in the program where you're not going to use this data structure anymore is to assign x the null value. You want to assign x to null at that point, and essentially dropping this pointer to the data structure. And now the garbage collector, whatever form it is, mark and sweep, stop and copy, reference counting, will be able to see that this is no longer reachable and will collect that big structure. And this is very, very common in production Java programs to have these kinds of memory leaks where you just have pointers that you forgot about to data that you're no longer going to use. So as I hope I've conveyed in the last few lectures, garbage collection is a very important technique. Every programmer should be aware of its benefits and costs, and it's also a very interesting aspect of programming language implementation. There are much more advanced garbage collection algorithms than we've discussed in these lectures, and the primary dimensions along which people have thought about improving garbage collection is making garbage collection concurrent, and that means allowing the program to continue to run while the collection is happening. So the collector is working in the background actively while the program is running. Another thing that's very common actually in production collectors is to have what's called a generational collector. And the basic idea here is that we don't want to keep going over and looking at objects that are very long-lived on every collection. So collections happen very frequently, and there will be some objects that just live for a very long time, the big data structures that hang around for most of the program. And once we've seen them in a couple of collections, we probably can assume that they're going to be around for a few more collections. And so in a generational collection, in a generational collector, older objects that have been around for a while are put in a separate area and they're collected less frequently. And this just allows the collector to focus on the objects that are most likely to be garbage, which are the recently allocated objects. We already talked a little bit about real time. So there are collectors that try to bound the length or bound the length of the maximum pause, the maximum interruption to the program. And finally, parallel collectors. So systems where there's actually several garbage collectors running at the same time and somehow coordinating their actions.